Hi everyone, welcome to this session to learn Kubernetes Networking and CNI. In this session, we'll explain Kubernetes Networking Model, Container Network Interface or CNI, and the comparison of common CNI plugins. Rancher comes with multiple CNI integrations, and we'll show you how you can configure that in Rancher. The goal is to help you understand Kubernetes networking and choose the right CNI for your use case. My name is Yuki, sales engineer. Louis Paul is also here with us. He's a cloud architect from SUSE. Networking is a critical component of Kubernetes. There's some terminologies on this slide. We expect you to have some basic idea of these concepts because our discussion today is based on these terms. Layer 2, Layer 3. Layer 2 uses MAC address to communicate between different servers. Layer 3 uses routing table, IP address, and routers to go to different networks. Overlay network is like a secondary network on top of your physical network. And VXLAN is a commonly used technology in overlay network to handle that pod-to-pod traffic between nodes. And BGP, a routing protocol used in non-overlay and encapsulated network. If you need a refresh on some concepts, you could just pause here and read through this reference. Some considerations around your network planning. Your Kubernetes nodes, control plane nodes, etcd nodes, worker nodes are assigned with IP address and subnet. There's also a pod network for pod-to-pod communication. And make sure your pod CIDR range is large enough to handle the size of your cluster and the nodes in each cluster. By default, it's up to 110 pods per node. You could also adjust that number. And service IP address range. The IP address range for all services in your cluster. You need to plan ahead based on your existing workload and the potential growth, because this IP address range is defined during the Kubernetes installation process and cannot be changed later. There's some basic principles of Kubernetes networking. Each pod has a routable IP address assigned to it. The pod can communicate with any other pod without using network address translation. Each pod knows other pods' IP address. The networking model is quite straightforward and doesn't need to do port mapping for the running containers. And Kubernetes is built on top of Docker, but it's different. Let's take a look at how Docker network works. It's the foundation for Kubernetes networking. By default, all containers can communicate with other containers on the same host. Docker offers different network types with different capabilities. First of all, host networking. In this model, the container shares the same IP address and network namespace with a host. And services running inside those containers have the same network capabilities just like they are running on the host. The host networking gives your containers the same IP address as the host. It's mapped directly to the host network. So there's no isolation between your container network and the host machine. Containers don't get their own IP address, and all interfaces and addresses on the host are also visible in the container. There's a bridge network on the right side. In this case, containers run in a private network internal to the host. The Docker daemon will create a bridge on your host machine, and when you launch a container, Docker creates a virtual Ethernet device within the container, like ETH0 you see here on container A, container B. And on the host side, it will create a unique identifier for that interface, like vETHXXS here. This interface is added to the bridge that Docker creates. And Docker maps the container IP on this bridge, and then your container can communicate with other containers that also use this same bridge on the same host. Network device running inside the container are not visible outside the host, so you need to run a command to map ports from the container to the host to make these services visible. And then container to container communication on the same bridge network If you're sending a packet from container A to container B, a packet leaves container A through ETH0 and lands on vETHXXX interface, which then connects to vETHYYY interface, in this case, through the bridge. And then the packet moves to the ETH0 interface in container B. That's bridge networking. And then there's also other mode like node networking mode. If your container doesn't need network access or doesn't need to communicate with other containers or with the outside world, you can disable networking. And then it won't be assigned an IP address, or it cannot just publish any ports. Other than that, you could also use a custom bridge network, which could provide better isolation, interoperability between containers. It also offers better security, more features. One example is the communication between our application container and database container without any external entities talking to the database. You could just create a custom bridge network for only database container and your backend application containers. Another one is overlay network, which virtually sits on top of your physical networks. We'll explain a bit more later. So Docker networking uses a virtual bridge network by default, which is defined per host and a private network. Bridge networks are for containers running on the same host. But in real life, applications usually require containers running on different hosts. And containers running on different machines cannot communicate with each other. So you have to map host ports to container ports and then proxy the traffic to reach across different nodes. And Kubernetes networking handles this quite differently. Kubernetes model supports multi-host cluster networking, and pods can communicate with each other by default, regardless of which hosts they're deployed on. This diagram shows the entire network for node-to-node communication and for container network. Linux kernel is responsible for translating between packets. And this diagram also shows you how the kernel handles connections. Routing, firewall relies heavily on Linux underlying packet manager. You could use static routes on your Linux server, so every node will know where to go to with a pod IP address. And Kubernetes uses some of these tools to handle node and pod connectivity and manage Kubernetes services as well. All these complexities are abstracted away. There are different ways to implement Kubernetes networking. Container Network Interface, or CNI plugins, provide more advanced networking functionality for network segmentation, scalability, additional support. So you don't need to configure many things like virtual Ethernet, static routes manually. CNI. Each CNI plugin uses a different type of model for networking. Some CNI, like Calico, uses layer 3 paired with BGP protocol to connect pods. Cilium, for example, could configure an overlay network with eBPF on layer 3 to layer 7. Louis will explain more about different CNIs later. There are two major network models used in CNI: encapsulated network model and unencapsulated network model. Encapsulated network or overlay network encapsulates packet from the underlay or your physical network that is routed to a pod on another node. Underlying network is not aware of your pod IP address or which pod are running on which node. The overlay network handles that pod-to-pod traffic between nodes. VXLAN is a popular technology for overlay network. It creates a logical layer 2 tunnel over a layer 3 network by adding IP headers for encapsulation. So this model reduces dependencies on your underlying network, meaning you can run it on top of almost any underlying network, and you don't have to change anything to your network. If you prefer to use an extended layer 2 bridge and have low latency in your data centers, then overlay is a good option. And then an encapsulated network is flat and assigns IP address to your pod. It provides a layer 3 network to route packets between containers. This model uses network protocol like BGP between nodes to distribute that routing information to each pod. Your pod IP address is routable across a broader network. It's like a kind of network router extended between your Kubernetes nodes. This model updates routes dynamically at the OS level. It's less sensitive to latencies. If you prefer to inspect network traffic more easily, then this model is perfect for that purpose. All right. Now, Louis will take over. He'll explain how each CNI plugin works, do some comparison, and get you how you could choose a CNI for your use case.
Thank you, for describing networking stack. And now our objective is to try to compare the different networking CNIs that are used with Kubernetes. So basically, CNIs comes usually in two flavors: overlay or non-overlay, supporting overlay or not. And the ones that we're going to cover today is the one that we see mostly in production environments. There are several other CNIs. I'm not going to go in an exhaustive list of them, but these are the ones that you most likely will cover. And also, from a Rancher standpoint, these are the ones that we support with Rancher deployments. So let's start with Flannel. Flannel, as you mentioned, has two modes, overlay or non-overlay. And the overlay can use different backends. VXLAN is commonly used in most cloud environments. Um, and that's the simplest one. It doesn't have to have any dependencies on any very specific uh, network configurations in the environment. And you can use it on private or secure networks since it's using some encapsulation and then creating the right tunnel to forward the traffic between the pods. Um, if you are going to deploy in environments where you are concerned about the security on the network, then Flannel also supports an IPsec backend. Um, that's the main considerations there. It can also be used in public clouds where you're not sure about the network in between the different components. In non-overlay mode, then Flannel has a host gateway, a backend that provides IP to IP traffic, and whereby there's concern sometimes about VXLAN and encapsulations. You might get some slight better performance by using the host gateway option. Um, Now, you also have the ability to be using very specific cloud provider CNIs. Um, Typically, they will be tuned for the by the cloud provider for the environment. But now the fallback or slight disadvantage is they are centric to each of the CSPs. So you may have to take that in consideration when deciding where to deploy. One of the big disadvantage with Flannel is unfortunately there's no network policy support. The second CNI that we want to cover is actually before we get to covering the next one, let's take a quick view how it looks like. Flannel creates an interface that on each of the nodes. Most of these CNIs run as daemon sets, so they create the stack on each of the nodes. And once the interface is created, then it uh, tunnels the traffic between the different nodes. It maintains the routing for the nodes using IP tables. Now, with Host Gateway, we mentioned it's not using any encapsulation, so there's no Flannel interface, and it's going through the host interface to be able to do the traffic. So where that might save some performance. Certainly, there's other considerations on what type of network you might be on, depending on private or secure. The second CNI that we see commonly in the field is Calico. The most commonly used use of Calico is for non-overlay layer 3 networking. It provides great performance. It's good to use in private data centers where you have some more controls over the environment. And one of the key factor with Calico is it can use the backend that will provide direct routing containers using BGP. So many enterprises they have some standard setup for networking, um, for router setup and maintenance. And if you want to take advantage of this, or you have a requirement to use and uh, operate in that environment, then Calico is a good choice. Um, by using BGP, of course, you can now advertise all your routes onto the common network where there might be other workloads. So it makes it very easy and clean way to have routing between not only your Kubernetes workloads but also external workloads. So this diagram shows you a bit on how Calico works and how it provides the IP to IP traffic and then publishes its routes using IP tables, but it publishes it to the route reflectors um, on the open network. The third one that I want to talk about is Canal. Canal is a project whose goal was to try to combine the benefits of Flannel and the network policy capability in Calico. Um, and there's been a little bit of less the maintenance over time with Canal. Calico project has tried to integrate most of the features back into Calico, especially the Flannel networking, and now it can use capabilities to have plugin chaining and have benefits of more than one of the CNIs. So although the project is not very active, SUSE Rancher has very good experience with Canal, and we continue to support it with our Kubernetes distros. Let's talk about Cilium now. Cilium is another common one, common CNI used. The big advantage with Cilium is it has taken a different outlook completely on how to provide networking. It's utilizing facilities that have been built in on the Linux kernel, in particular eBPF. And by going that route, it in a sense simplifies how the networking routing and how you can manage the rules and how you can have observability over the traffic that's going on between pods. So that like it says here, it includes identity-aware security. It can do multi-cluster routing. At that level, it can do transparent encryption, and it's got ability to use all types of filtering of the packets so that it can actually throttle or manage the network at that level. So eBPF also uses the Cilium CNI uses eBPF in order to enforce network policies. So it can write rules that are based on eBPF. So tutorially here shows how there's no more of manipulating and creating a virtual Ethernet interface that has to go through the IP table chain. Instead, the Linux routing is handled completely by the eBPF. And that is another picture that shows how that works across different nodes as well. So that previous one was just a single Linux stack, how it differs, and then the other ones are across stacks. So by using eBPF, you now bypass IP tables, as I mentioned earlier, and you eliminate a bit of this overhead that is maintained within the namespaces of each of the containers. On the egress side, then the routing table is consulted, that is maintained by eBPF, and it can do additional level of optimization on egress to channel the traffic between the pods. So, at a high level, a lot of these CNIs have their benefits, but if you were to try to narrow it down to like a small decision factor, you would look at Flannel from a standpoint of it's been used, it's the most battle-tested CNI. It has done well in many private and public cloud environments. It's got a good set of capabilities in terms of supporting overlay or non-overlay modes with multiple backends. And the only disadvantage here is it does not support network policies. Calico picks up from that with network policy management, and also with the ability of being able to do the routing directly, publishing routes onto the BGP based routing network. And so that might be a important decision and requirement when deploying in enterprises. Might not be as common to use it, let's say in cloud environments where that might not be, BGP might not be used as much. Canal is a good option. It's well supported by SUSE Rancher, and that's when you're looking for additional network policies on top of what you typically get directly with just Flannel. And Cilium could be a good choice if you're trying to get an implementation that is using everything based on Linux kernel capabilities. So over time, it might get more interesting with the with the what gets done at Linux level. And also that you can then start, since you're dealing with packet level traffic, you can apply different levels of policies at layer 3, 4, or 7. So if you had to put it in a table, this is the different CNIs you just mentioned, and these are the different levels of support. We didn't talk too much about vendor support, but that would be something quite important for you if you're deploying in a enterprise and you have some important requirements to be able to have full vendor support behind the implementation. And all of them deploy a daemon set, so I think we talked about this a bit earlier. Another factor to try to compare these CNIs would be to look at how much bandwidth they use, what amount of resources they are consuming, and also some performance. There is the information that's displayed here is from a source on GitHub, so you could take those benchmark and run it into your environment to see how it fares in your own. But overall, as we can see, most of these implementations have pretty good performance. Where they differ a little bit is in terms of manual configurations. It's a bit of tweaking that you need to do with MTU settings. It's common with Calico and Canal. Canal because it's using Calico as well. Um, and and then there is resource consumption. It comes out that with Cilium having to do a lot of the manipulation with eBPF, the runtime usage tends to be quite high. Otherwise, all the other CNIs seems to compare favorably. And again, what you might want to look at also is the security capabilities of each of them. So we mentioned earlier that Flannel doesn't have network policy support, so it won't fare well there. Um, and also with Canals, which is using Flannel. And then there's some consideration also in terms of the configuration, dynamic configuration that you may want to do on some of those plugins. So back to you, and you can show how in Rancher we configure the CNIs.
All right. Thanks, Louis, for your detailed comparison. Rancher supports and integrates with common CNI plugins very well. We provide Canal, Flannel, Calico, Weave for RKE, and Canal, Calico, Cilium for RKE too. It really depends on your project, like Louis just mentioned. Canal is the default CNI, so if you don't know much about your use case, or if you really don't have a preference or any specific goals, we recommend Canal for most use cases because it provides the functionality from Flannel for overlay network and Calico for network policies, which offer project and namespace isolation in the network space. In the Rancher UI, when you launch a new downstream cluster, you can just choose the CNI you want to use. If you like to do more advanced configuration, you can use a config file as YAML, which allows you to add more parameters, something like specify the type of Flannel backend to use, to add that customized configuration. Anything supported by standard Kubernetes will work in Rancher. All right, that's an overview of Kubernetes pod networking and different CNI options. That's like traffic in a Kubernetes cluster. Moving forward, you also should address how traffic from outside of your cluster finds its way to the destination. And keep exploring how services work, how Kubernetes approaches load balancing and DNS. Discover if you need a service mesh for service-to-service communication. Those are all areas you should look into. All right, everyone. I hope this session helps you clear some questions about Kubernetes networking. Hopefully, you have an idea which CNI works better for you. Thanks for joining, everyone. Bye.